Good morning. This is our second lecture on the lecture series on X-ray crystallography and solid-state chemistry. In this lecture, we'll deal with solids, crystal lattice, and crystal symmetry. That might take a few lectures of 20 minutes. So let's start our lecture. The syllabus content of the first lecture was the solid, properties of solid, crystalline and amorphous solid, distinction between crystalline and amorphous solid, classification of crystalline solids, isomorphism, polymorphism, and we finished our 20 minutes by talking this. Now I'll go the last of one of this chapter, that is allotropy. Well, we discussed polymorphs, where you say the same compounds having different structures, we call them poly of the compound. Similarly, if it is different structure of same element, we call it allotropes. I showed one example of allotropes of carbon. You see, carbon has got crystalline forms: diamond, graphite, fullerene, graphite. If we go for amorphous form, we call it coal, charcoal, coke, lumpback, gas carbon. So many elements in periodic table have allotropes. We take only few examples here: oxygen, phosphorus, tin, and iron in the next slide. Oxygen has got polymorphs. We know dioxygen, ozone, tetraoxygen, octaoxygen, delta phase of oxygen, chi phase of oxygen, metallic oxygen. But metallic oxygen we only get at very high pressure. Similarly, if we go for phosphorus, we say that white phosphorus, red phosphorus, violet phosphorus, scarlet phosphorus, black phosphorus, diphosphorus gas form of phosphorus. We go for metal, a few metal, tin and iron. Here you see alpha tin, which is cubic crystal, beta tin, which is white tin, known as white tin, gamma tin, and delta tin. You see. Similarly, for iron, we get alpha iron, which we call ferrite, gamma iron, austatine, and delta iron, body-centered cubic iron, chi iron, or hexaferrum. So this is what is allotropes, and I say many elements do form allotropes depending on temperature and pressure. Well, if we want to discuss crystal lattice, crystal symmetry, etc., then I believe we have to which are the books or website I'm following to prepare these lectures. Many standard textbooks we have, and monograph too, as well as we get PowerPoint presentation, which you can download from internet, and principal applications of X-ray crystallography. These are the books I'll be following when I prepare lectures of this series. X-ray method. Well, we get many interesting papers or publications about crystallography in the website of International Union of Crystallography. Here is the website. I'll mention simply, this slide is about International Union of Crystallography, but you will get it if you go to the website of IUCR. But I have to mention here that IUCR website has got a tab, education. Under this tab, you will get teaching pamphlets. And there are 23 pamphlets. It's free of cost, one can download. And there you have many excellent materials for advanced crystallography and as well as elementary. this slide specifically, I'm talking about history of crystal. So this is definitely not in syllabus, but to make you a little bit interesting in crystals, we see that about 9,000 years back, people in Mesopotamia, they used quartz crystal as jewelry. How the term crystals come, ancient Greek philosophers, they called crystallos as ancient Greek word pus, and this means icy cold. And probably there we start talking about crystal. Well, Chinese people do use crystals for their traditional medicine at least 5,000 years back. Ancient Egyptian lapis lazuli, tracuzi, and several other crystals have information, and they use it in jewelry, as well as to protect their health. Crystal like galena, malachite is used for cosmetic purpose. Green stone, that's the very important information. They used to signify the heart of deceased person and included green stone as burial's purpose. That also was seen in ancient Mexico. There are the two crystals at that time I showed in this slide. The greatest talent of Arabian geologist, sorry, I didn't get his name, but he was investigating the problems of tessellation of two-dimensional space. And that was the very important contribution of crystallography and geometrical art. Even today, people used his geometrical art to teach symmetry all over the world. Well, Greek philosopher was I wrote his born and that he is on his treatise on stones classified and classified the properties of rock and gems. Well, then another philosopher, Roman philosopher, that was very difficult for me to pronounce his name, but he was normally called Pliny the Elder. He, in his article in the Natural History, described that the windows and greenhouse of rich inhabitants of Roman Empire covered very large transparent crystals of gypsum. Well, the first mathematical description about crystal is given by John Kepler, the German mathematician, astronomer, and astrologer. That was the first mathematical description on his article, that is six-cornered snowflake. Danish Catholic Bishop Niels Stensen, he wrote an article where the fundamental crystallographic law, which we call constancy of interfacial angles, that was the development of today's crystallography, I would say. In 1783, law of constancy of angles was confirmed by a French mineralogist with many other crystals. Then comes who is a professor at Paris University. He elaborated his article on this. This is the French article, which was the solid pillar in construction of crystallography. And his article, if we read now in English, we can see that today's crystallography does not much differ from his article or so. Then there are many crystallographers who started crystallography using laws of Hugh and developed crystals and crystallography further. The German physician I say, looks at physicians, mineralogists, physicists, mathematicians, chemists, all contributed on crystallography. And German physician Hessel, he, with the help of Hughes law and morphological form, said there are exactly 32 kinds of crystal symmetry, which we call today 32-point group. And then German physicist and mathematician Frankenheim, who deduced 15 unique three-dimensional lattice of crystals. But unfortunately, after 3 years, in 1848, French physicist Brabais, he corrected that deduction and showed it is not 15, it is 14 unique three-dimensional lattices, which we call today Brabais lattice. And then this was the eminent Russian crystallographer Fedorov, and also German mathematician Arthur Schoenflies. They used this 14 Brabais lattice and 32-point groups, which I talked earlier, and deduced 230 possible space groups. These 230 possible space groups restrict the building unit of crystal, that is atom, ions, or molecules inside the crystal. Now we go for our crystallography lecture. That was simply a history, how it developed. Then mineralogists used to classify mineral crystals. And they say they have found crystal families. And they gave relationship between axial parameters of crystal families. But mineralogists showed one, isometric, tetragonal, orthorhombic, monoclinic, anorthic, and hexagonal. That means 6 crystal families. But today, when we study crystal with the help of three-dimensional reference accesses, we see that there are unique 7 crystal systems, not 6. So mineralogists missed the one crystal system, which is trigonal, or also called rhombohedral, and the cell parameter of trigonal and rhombohedral is this: A is equal to B, B is equal to C, alpha, beta, gamma is not equal to 90 degrees. I come to it in next slide, but simply showing mineralogist classification, and then there are minerals they found within each classification. For example, fluorite, olphinite, tanzanite, azurite, amazonite, emerald. And then this one, this trigonal rhombohedral, which they missed, is also we find minerals in this system, rhodocoprosite, which is manganese carbonate. I gave the chemical composition of all these minerals here for your information. Here are the crystals of 7 mineral crystals of 7 crystal system. Fluorite, which is cubic, then olphinite, which is tetragonal, and tanzanite, which is orthorhombic, azurite, monoclinic, triclinic is amazonite, and hexagonal is emerald. That one was missing in the crystal family of mineralogists, rhodocoprosite, which is rhombohedral. Now we go for crystal lattice and crystal symmetry. We will talk this in next few slides. Here we are showing some lattice points. That white dots are lattice points. And in these are crystal planes. We show crystal planes, different types of crystal planes, and different 2-dimensional unit cell here. So a unit cell means that we can talk about unit cell, the smallest identical lattice points, which can be constructed in 2-dimension or 3-dimension, and repeat this unit And then that smallest unit we call unit cell. We come to it in the next slide with three-dimensional well, we talked about lattice and unit cell of a two-dimensional system in the last slide. But now we are coming to three-dimensional systems. You see, this is how we will define unit cell parameters. With this diagram, we will define unit cell parameters after a few seconds. But here we can see that this is the unit cell. And when we repeat this unit cell three-dimensionally, it becomes crystal lattice. That means unit cell is the smallest part of a three-dimensional crystal lattice. How we define this unit cell then? We will take a three-dimensional coordinate system. We know that in mathematics, we use x, y, z as three-dimensional axial parameter, and also angle alpha, beta, gamma. But for crystallographers do use in their own three-dimensional system, identifying axial parameter as A and B as Y and C as Z. And that's what we call a right-handed three-dimensional system, taking thumb as A and then pointer as B and ring finger as or middle finger as Z. That is what is the convention of defining crystal systems. So by defining these crystal systems, we have 6 parameters, 3 axial parameters and 3 interaxial angles. A trick I want to show here that when we have axial parameter A and C, if we compare A, B, C as English letter, alpha, beta, gamma as Greek letter, and then we see A and C axial parameter, missing is B. That means Greek letter beta will be the angle for this. Similarly, you come to C and B, missing is A. So axial interaxial angle will be alpha, and similarly gamma also. So using these 6 parameters, we can have unique 7 crystal systems. So cubic crystal system, as we say, alpha is A is equal to B is equal to C, and alpha, beta, gamma is 90 degrees. We continue like this, and we'll say that we can develop mathematically unique 7 crystal system. So this is the unit cell parameter of all the 7 crystal systems. One thing we have to remember that only unit cell parameters definition might give you some wrong idea about crystal system. We have to remember all crystals have symmetry. All crystalline materials have symmetry. So we have to consider symmetry also to define unit cell crystal system correctly. Sometimes we may see that there are unit cell parameters is saying that it is a cubic crystal system. But if you go to essential symmetry elements and may see that the essential symmetry elements of cubic crystal system is missing, in that case, we cannot call this cubic crystal system. So both cell parameter and essential symmetry systems must be taken into consideration to define crystal systems. We have to remember this. And another thing we have to remember that for molecular systems, we can have 2 settings. The most normal setting is given here, and the other setting when we have A, B, C are not equal to each other, and alpha, beta, gamma is 90 degree. Alpha, beta is 90 degree, and gamma is not 90 degree. Here you can see that beta is not 90 degrees. So this is the convention generally used, but sometimes you can see that this setting for monoclinic is also used. And now we go for next one, that is base lattice, unique lattice, which we must have to know before we go for the symmetry. So I think this would be almost the end of the second lecture. We will take this part of the base lattice in the third lecture, and symmetry and so on. Thank you very much for this listening the second lecture. We'll be coming within a fortnight with the third lecture, where we'll also discuss crystal lattice and crystal symmetry. Thank you so much.